Hi, and welcome to Part 4, Solubility Equilibrium, in our discovery of reaction rates and equilibrium. Many times, if people go to get an X-ray done of their intestine, or their GI series we call it, they give them some barium sulfate, which is a poison. Okay, but it can absorb X-rays, so you can see what happens. So these tissues, which usually wouldn't see in an X-ray, all of a sudden they appear in an X-ray. How is this possible? Any ideas? Well, it must be something about the poison. There isn't enough of it to make you sick. So one of the things we have to look at is solubility. Solubility is the ability for something to dissolve in a liquid or in another solid or a gas in a gas. But basically, usually when we're talking about solubility, we're looking at solids in a liquid. And usually that liquid is water. So we have what's called a solubility product constant, which will tell us if something tends to be very soluble or not soluble at all. All right, we'll learn a little bit more about that as we go along. So we know that most alkali metals that are part of an ionic compound will be soluble in water. So for instance, if I gave you 35 grams of sodium chloride, it will dissolve in 100 grams of water. On the other hand, some ionic compounds are insoluble in water. For instance, compounds that have phosphates or sulfites or carbonate ions are not easily soluble in water. They'll just stay in their solid form. So here's a table that summarizes some of the solubility rules for ionic compounds. So anything in group A, 1A, metals and ammonia are soluble. Now there are a few exceptions. Some of the lithium compounds are not soluble. Things that are ethanoates, nitrates, chlorates, and perchlorates all tend to be soluble. The most important one of that is nitrates and the chlorates and perchlorates. Sulfates are soluble except for those with the metals on the right-hand part of the table. Chlorides, bromides, and iodines are all soluble except for silver, mercury, and some lead compounds. Sulfides and hydroxides are usually insoluble, meaning they don't dissolve very well. Remember, though, that that's trumped by the alkali metal sulfides and hydroxides are soluble, as well as ammonia compounds. And compounds of barium, strontium, and calcium are slightly soluble. Carbonates, phosphates, and sulfites are insoluble except for the ones from group 1A metals and ammonium ions. That summarizes solubility rules. But what does insolubility mean? Actually, a small amount of the compound is soluble. So it's very slightly soluble in water. And this is where the solubility product will come in. For instance, silver chloride will dissociate very slightly into silver ions and chloride ions, but the majority of it will stay as a substance at the bottom of the test tube or beaker. What happens is an equilibrium will be established between the solid and the ones that have dissolved. There'll be a lot more of the reactant, the silver chloride, than there will be of the silver and chlorine. Now notice, in this case, one thing you should note here is this is a solid. That would be the reactant, but we don't really consider reactants that are solids as part of an equilibrium expression. So normally we would write this times this over this, but this is considered 1, so it's not part of the equilibrium expression. So here we are. Oh, let me go back. So if we look, normally we would write our KEQ like this, but we're going to kind of throw this guy out. So we use solubility product because that amount of AgCl is a constant, so we just kind of bundle it into this new K with a little SP, meaning solubility product. Okay, so it's still the same idea, but KSP is just the concentrations of the products raised their appropriate coefficient. If this number is large, then the solubility product means it's very soluble. Okay, if it's small, it means it's pretty insoluble. So soluble, insoluble. All right, and there we go. The smaller numerical value, the solubility constant, the lower the solubility of the compound. Here's a table of KSP values, and you could use this. I would take a screenshot of this for any problems you have for solubility products. Those things that have a large negative number means it's a very, very small amount. So these are pretty insoluble. Okay? Things with really big numbers aren't there because they tend to be the very soluble things. Okay? When you get in the range of like from 1 to 50, or even 0.10 to the minus 2 to 50, you're talking things that are basically at equilibrium, a normal equilibrium expression. Okay, how can we use this to solve for ion concentrations? All right, so we know the KSP, and we know we have lead and chromate. So if we basically look at what lead and chromate is, we have to look up lead 2, so that has a +2, and chromate, we'd have to look up its number. So there we go. It's also 2-, so it's a 1-to-1 ratio. Okay, so we know that from the balanced chemical equation, the molarity of the lead and the molarity of the chromate should be the same. So that means it's the same value, and that's going to equal our KSP. So all we have to do is write it out like here. Okay, that's the KSP value they gave us. And now what we have to do is, since these two terms are the same, all right, so we can think of that as X and X. Rather than change it to PB and PB, I would do it this way. So X times X equals X squared, and then you would just basically solve this by turning that into a square root. Okay, so let's continue. So there we go, and so we find out that it's 1.3 times 10⁻⁷ molar. That would be true for lead, and it also would be true for the chromate. You could check it to see if you ended up getting the same answer when you plug that in, and if you did that, you would get 1.7 times 10⁻⁴, which is close enough because we probably rounded a little bit. All right, here's a question for you for Educanon based on this chart. So you might want to take a screenshot of that chart before I turn off this. So take a quick screenshot of this. All right, and I'll catch you on the other side of the Educanon question. Hope you pick zinc sulfide.